Hey there, let's talk about something that's literally all around us, but at the same time, almost completely invisible. It's the science of surface engineering, and it's all about how changing just a few atoms on the outside of an object can completely change everything it can do.
I mean, have you ever really stopped to think about this stuff? How can we put a piece of metal, a hip implant, inside a person's body, and the body just accepts it? Or how do the parts inside a jet engine put up with temperatures that should turn them into liquid? These are pretty high-stakes situations, you know? Failure is not an option.
And believe it or not, the answer to both those questions is in the exact same place, the surface. It's not just about what the material is made of, but how we've cleverly engineered its outermost layer to deal with the world.
Which brings us to our first big idea. What we're really talking about here is giving ordinary materials, well, superpowers. It's kind of like performing a tiny bit of surgery right at the atomic level.
The basic concept is actually surprisingly simple. You take a material that's already got great qualities. Maybe it's super strong or incredibly light, but it's got a fatal flaw. Maybe it rusts, or maybe our own bodies attack it. So by re-engineering just those top few layers of atoms, we can give it brand new abilities without messing with any of its core strengths.
So what kind of superpowers are we talking about?
Well, we can make a titanium alloy implant, something like T64, biocompatible, so your body welcomes it instead of fighting it. We can make steel almost completely immune to rust. We can make machine gears so hard that they barely show any wear and tear. We can even create surfaces that kill bacteria like E. coli on contact, or surfaces that are so hydrophobic that water literally just beads up and rolls right off.
Okay, this all sounds pretty amazing, maybe even like science fiction. But how do they actually do it? Well, that leads us right to the scientist's toolkit. Let's look at the actual processes they use to pull this off.
When you dig into all the research with all the complex-sounding techniques, it really all boils down to two main ways of thinking about it. Just two basic approaches.
All right, so the first approach is to simply add a new layer. You're applying a specialized coating right on top of the original material. The best way to think of it is like painting on a suit of high-tech armor. The second approach is totally different. You change the existing surface itself. Here, you're actually altering the chemistry or the structure of the material's own atoms. So instead of painting armor on, it's more like forging the armor directly out of the existing metal. Both are incredibly powerful, just used in different ways.
And the list of tools for adding a layer is just incredible. You've got things like plasma spraying, which is basically an insanely hot spray paint gun that shoots molten material, or laser cladding, which uses a powerful laser to literally fuse new material right onto the surface. Then there are even more precise techniques like magnetron sputtering and pulsed laser deposition, where scientists are building up these new surfaces atom by atom inside a vacuum. It's amazing.
Now, on the other hand, if you want to change the surface itself, you've got a whole different set of cool tools. Laser surface hardening is exactly what it sounds like. A laser zaps the metal, heating and cooling it super fast, which makes it way tougher. Plasma nitriding actually infuses nitrogen atoms into the surface to create this incredibly hard layer. And then you have methods like surface mechanical attrition treatment, or SM8, which basically use force to rearrange the material's own atoms into a much stronger structure. So, okay, we've used these incredible tools to create a new surface. But how do we know it actually worked? Right, it's time to look under the hood.
And this is a really crucial step. A lot of these engineered layers are completely invisible to the naked eye. I mean, we're talking about changes that are just a few atoms thick. So how in the world can anyone be sure that the new superpower is actually there? Well, the hero tool for this job is the Scanning Electron Microscope, or SEM. Seriously, it came up in almost every single research paper we looked at. Instead of using light, it fires a beam of electrons to scan the surface, and it produces these incredibly detailed, highly magnified images.
Really, it's like having a camera that can see atoms. It lets scientists zoom right in, past the microscopic texture, all the way down to the nanoscale grid of the atoms themselves. This allows them to literally see the new surface they've built and confirm that its structure is exactly what they were aiming for.
And the SEM is just the start of the inspector's gadgets. To see the structure, they have tools like atomic force microscopy. To check the chemistry, to make sure the right elements are there, they use things like X-ray diffraction. To test for toughness, they use techniques like nano-indentation, which is basically poking the surface with a microscopic diamond point. And finally, they have to prove that it works with real-world challenges, like corrosion tests or studies to see if living cells can thrive on a new implant material. And here's the proof. This is what all that testing leads to. You can see the untreated material on the left just getting wrecked by corrosion. But look to the right. After the treatment, that corrosion rate has absolutely plummeted. That's what success looks like. That's the superpower in action, proving all that complex science was totally worth it.
So this leads us to our final thought. What does all of this actually mean for us, for the world we live in? What's the real impact of engineering these invisible surfaces?
The applications are honestly staggering. This isn't just something that happens in a lab. From the tools in an operating room to the components on a satellite in deep space, this science is quietly building a world that's safer, that lasts longer, and that's just a whole lot more efficient.
The impact really is everywhere you look. In medicine, it means implants that heal better and last for decades. In the energy sector, it means more efficient turbines and infrastructure that doesn't just rust away. In electronics, the chip in your phone is made up of dozens of these specialized, ultra-thin layers. And in manufacturing, when tools and dies resist wear, it makes everything cheaper and more reliable to produce. And we can even put a number to the benefits. Applying the right surface treatment can increase the lifespan of critical machine parts by over 50%. Just think about the impact of that on cost, on safety, and on reliability across pretty much every industry.
So, yeah, from making a hip replacement feel like it belongs in your body to ensuring a plane engine works flawlessly, it all comes down to engineering the invisible. Which leaves us with one last big thought. With this incredible toolkit at our disposal, what problem are we going to solve next by engineering the perfect surface? Thanks for tuning in.